discussion. We have a bit of time, so what we'll do, we'll still stick to the 12-minute presentation with three minutes for questions, and then if we have time at the end, we can have a little bit of discussion. So actually, the first talk is by my co-chair here, Heather Andres, and she'll be talking about the timing and controls of spring restratification on the Newfoundland and Labrador shelf based on GLORIS 12 version 1 data. And I also want to mention that we have 3 posters in this session, so tomorrow morning, don't miss those. And I'll invite Heather to start her talk. And oh yes, I just wanted to say that I'll kind of flag at 3 minutes and then at 1 minute and at 0 minutes, and then we can start. Oh yes, and for people online, welcome as well. And we have Q&A and chat. Please potentially put your Q&A, your questions in the Q&A so we can monitor those. So. Oh, yes, and I forgot to mention there is a 30-second lag between what's happening here and what's happening online, so we just keep that in mind.
Hello, everyone. It's a pleasure to speak to you this morning. Oh, apparently my first screen won't come up. All right, I'll be speaking to you today. Colleagues of mine at DFO in Newfoundland and Labrador, as well as Dr. Frédéric Cyr and Peter Galbraith, are pleased to talk to you about some work we've been doing about looking at stratification in the Newfoundland and Labrador region. So for background, the spring phytoplankton bloom forms the basis of the marine food web in the Newfoundland and Labrador region, and some work has been done previously to try and assess how you can relate the timing of this phytoplankton bloom to physical oceanographic conditions. And some initial work by Wu et al. In 2007 linked the timing of the spring phytoplankton bloom at station 27, which is, let's see if I've got, I kind of have it, which is the red star near on the coast of Newfoundland, to sea ice retreat. And more recently, Dr. Frédéric Cyr has linked it instead to timing of the stratification minimum or the initiation of restratification in the spring. Now, observational data sources in the region are predominated by the Atlantic Zone Monitoring Program, which was designed to monitor interannual variations in oceanographic conditions. It primarily includes 3 surveys a year at set transects, which are marked on the plot in the red dots and the red labels. But unfortunately, this is insufficient temporal resolution to be able to capture changes in something like the timing of a spring restratification at any locations other than at station 27. So the goals of this work is to use model data to characterize spring restratification, timing, and controls on the Newfoundland and Labrador shelf. And then that's going to include some evaluation relative to the AZMP observations where we have them. I'll present the stratification seasonal cycle at these transects and analyze the contributions from surface freshening and heating via an alongshore transect, and finally do some initial exploration of the relationship between the timing of the restratification and sea ice retreat in the model. So the model I'm using is the GLORIS 12 Global Ocean Reanalysis, which spans years 1993 to 2020. I'm not going to give you a lot of the details here, but I will point out that the runoff is based on a monthly climatology based on years 1948 to 2004. There is some attempt to try and capture the impact of freshwater hydrological changes that are ongoing through the application of an open ocean freshwater flux that's prescribed at a fixed rate. That's supposed to try and compensate for or capture some of the impact from icebergs, ice sheet melt, and other land water storage changes. The data that's assimilated is predominantly from satellite fields, sea surface temperature, sea level anomalies, and sea ice concentration, but it also includes the in situ temperature and salinity profiles, which includes the AZMP data itself. So I'll show you some initial evaluation that we performed. So we calculated stratification, in this case, as the buoyancy frequency in the model. And I've plotted here on the right, on the vertical axis, the modeled buoyancy frequency versus the observed for 3 seasons, spring, summer, and fall when we have AZMP data. And the different colors for the dots represent the different transects. And this work was published just recently in a paper last year. And what we showed, for each transect, we create a single stratification value. It's based on the vertical maximum stratification at each station, then averaged across all stations in a transect. And what we found was that there were significant correlations in the interannual variations between AZMP and Glorious 12. We're getting values between 0.7 and 0.9. However, as you can tell by looking at these plots, the Glorious 12 significantly underestimates peak stratification by a factor of up to 3/4. Now, I'm showing here the climatological season pattern for stratification. Again, buoyancy frequency in the y-axis. On the x, it's the week of year. And the lines here are based on Glorious 12, and the different colors correspond to the transects, where we have the most northern transect from the top moving down southward. And the shading around those lines corresponds to the interannual variation. The dots are colored and indicate the AZMP data value from a given year. So you get a sense of both the observational data and the model data on this field. And what you can see is that stratification really starts increasing first in these northern Newfoundland transects, but those changes are very, very weak for quite a while. Whereas what we see in the model is that the stratification peaks earliest at the most upstream transects on Labrador. So this is Beechy Island and Makkovik Bank. If we look at the timing for the stratification decrease in the late summer, then what we see is that proceeds initially at most northern transects and then on down southward. So to then analyze the contributions from temperature and freshwater to this stratification field, I've created a longshore transect, and that's marked here by these purple dots. Where this transect intersects the AZMP transects, I've used the AZMP station as my reference. And I've decomposed the contributions or estimated them from temperature and salinity via the equations here, and those are plotted here. So on the leftmost panel, this is the maximum stratification at each station, so vertical max. In the middle is the contribution from salinity, and in the right-hand side is the contribution from temperature. And at the top of the zero, essentially for distance, is northern coast, the northern part of Labrador Shelf, and it proceeds down here. And the different lines correspond to the transects. So these three are all from the Labrador Shelf, and the rest of this down here is all the Newfoundland Shelf. And what we see is, particularly in northern Labrador, that restratification is preceding any noticeable heating. Instead, what we see is there is a significant contribution from freshening at that time period. If we look at the contributions for temperature, we see that they are occurring at pretty much the same time of year for all of these transects, regardless of where they are north to south. And you can see the signature of that in our total stratification. However, this is much later than it's in the midsummer, and it's much later than the typical timing we would consider for phytoplankton bloom. So here I've taken in these yellow boxes the estimated times or typical times for phytoplankton bloom start and peak. And this is published from Sierra et al. 2024. And what you can see is except for this station here on the Labrador Shelf, the rest of the time period we're actually interested in precedes any really strong stratification. So we're looking at a period of very weak signals. And if we look at our contributions, then really the only contribution we see is from freshening, which raises the question of the role of sea ice during this stratification initiation. So to examine this further, I've wanted to define a time for restratification, and I want to define a time for sea ice retreat. So I've defined spring restratification as the first day after we reach the minimum and the vertical maximum buoyancy frequency, where we exceed 10% of the range between the minimum and the maximum for a given year. So that threshold would be different each year. And the minimum is marked then in these black lines, and the restratification date is then marked in the red lines. And I've calculated this timing both from GLORIES 12 and from the AZNP data at station 27, which, as I said, is the only station we have observational data of sufficient temporal resolution to be able to compare. And what we see is, if we look at the general trend of stratification, change and growth and maximal value throughout the year, what we're looking at is something that's actually quite earlier than most of that. So like I said, this is a period of very weak change and very short-lived. And you can see in both the model and in the observations, these are short-lived events that we're talking about that are coinciding with our typical phytoplankton bloom timing. And if there's a challenge, okay, if we look at sometimes our observational data is sparse, and it looks like that got cut off by the thing. So I'll just move on. So what happens here is you can see that sometimes we measure this point, but then it turns out that actually there were no data points prior to that. So we really can't judge where in that period it would have happened. So when I compare those and I plot the modeled stratification timing versus the observationally based ones, we see we actually have fairly good correspondence for a subset of the data, and a subset of the data shows GLORIES underestimating the observed timings. So timing of sea ice retreat is given by when we reach 10% less than the maximum sea ice area or volume or thickness for that year. And that is a very noisy signal if you look at smaller areas, and it can sometimes be very difficult to say this is clearly sea ice retreat. So if I plot then my restratification date assessed on a grid cell basis on the left here, averaged over all years, and I show the sea ice retreat dates averaged over all years on the right, we see a few features. One is the earliest dates are here at the outflow of Lake Melville, and the timing there greatly precedes that from sea ice retreat. That is a general trend for all of the Labrador Shelf. We're seeing that the timing of restratification is much earlier than the timing of sea ice retreat. That's whereas over the northern Newfoundland Shelf, the timings are pretty similar. And based on the White Bay transect, which is given by these dots, we see a weak but significant correlation with sea ice retreat over just north of that, upstream of that in the southern Labrador Shelf. So essentially, what we're seeing is that we have, in the model, there are seasonal patterns of stratification that depend where you are. The timing of the phytoplankton bloom, only surface freshening, appears to be contributing to this weak stratification. Based on the analyses I've performed, there's little evidence that sea ice is playing an important role there. We see the earliest stratification at where we have freshwater export in the mouth of Lake Melville and also Hudson Strait. We see the Labrador Shelf. The sea ice retreat is occurring much later than the restratification, which raises the question about potential for under ice blooms. For northern Newfoundland, there's a potential based on timing that there could be a relationship. But I want to note, and this is for future work, that sea ice melt can occur without a sea ice volume change due to the advective nature of the conditions in this area. So a future work is going to look at the actual sea ice, try to quantify the sea ice melt that's occurring in the model as opposed to just the volume changes, and then see if we get a better relationship there. So thank you. Oh yeah, okay. So if you have any questions, we have a microphone for those in the room. If you're just too eager, I can repeat the question as well.
Okay, thank you very much for your talk. And I just have a question because I didn't understand the stratification. So you showed the stratification as a histogram over time, and you showed the salinity contribution and temperature contribution. But as far as I could tell, the salinity plus the temperature didn't equal the density.
They don't.
So what am I missing?
That is an open question right now. We're trying to work out. So we were calculating them using two different methods. And I think the difference there is we're using, like I said, the equations I showed for the temperature and salinity components. And for the total, I was using the GSW built-in n-squared calculator, whereas these other ones I was calculating separately. So there is a question mark there as to why they don't add up. And it definitely doesn't.
Thanks very much.
I have a question, but also I'm just going to comment on the last one. GLORIES uses data assimilation. Maybe this is an assimilation term taking place in those calculations. But I was going to ask, when you showed the restratification timing compared to the melt timing,
Yep.
I saw very nicely there were two pathways. Yeah, the red,
Yes.
especially along the inshore, then the shelf break,
Yep.
Labrador Current, which to me is suggesting then that fresh water is actually a signal maybe of the previous year's melt and runoff in Hudson Bay and or farther off that's then being exported.
Yes.
Is that likely what you're seeing?
Yep. And I think this is without me having done any look, when I look at this, what I'm interpreting is exactly what you're saying. You see the Hudson Strait outflow right here, and you can see it kind of following along the coastline here. There's little connectivity originally here, but from this point along, you can see all the water that would be coming off the land right there. But what's interesting, I think, is what's happening around Lake Melville. Well, we have a source term, essentially. And there you can kind of see some pathways where this water is mixing out off to the outer shelf as well. And but as well continuing along in through Strait of Belle Isle, etc. So there's definitely, yes, I would say what we're seeing is very much an advective regime happening.
Great, thank you.
Okay, thank you.
So thank you very much, Heather. If you have questions, you can put them in the chat and maybe we can address them later on in the discussion part. We'll try now to move on to under climatological forcing conditions. Jared is joining us virtually online, and we did have a few issues with the sound, so we'll try to see if that works now. Jared?
Yeah, can you hear me now?
Oh, yes, that's good.
All right, I'll explain later.
Wonderful. Did you try the music?
I'll explain later.
And I think you're going to need to share your presentation from there, Jared, is my understanding.
Oh, I thought it was being shared through the other end.
If you want, I'll open it up.
Yeah, if you could open it up from that end, that's, yeah.
Okay, I'll do that. Okay, so I have to share. Where's the share button on this one again? Oh, here it is. Share screen. Okay. Okay, thank you. Okay. And go and okay.
Yeah, I'm seeing presenter mode. Hello? Sorry, can y'all hear me now? Okay, just go ahead. Sorry, I'm not getting any confirmation. I can't hear right now. If someone could just drop in the chat whether or not to start. Room, I'm not sure if you heard me, but I can't hear you right now. So if you could just drop in chat when I'm good to start, I'll just go ahead. Oh, okay, wonderful. Sorry, I can't see the slides now.
It's okay. No, I can't see it there.
Yeah.
We can see it online. Okay. Just maybe
I'll go back to the entire screen.
the entire screen.
Okay, I see slides. I think people can hear me. Are we good? Yeah, I'm just going to go ahead. Okay, hi everyone. Today I'm going to talk to you about some biophysical modeling work that we've been doing to simulate the spring phytoplankton bloom near the coast of Newfoundland. So this project was funded a couple years ago under DFO's Competitive Science Research Fund. The proposal was spearheaded by Nancy Soontiens, which allowed us to hire Chung Chen for a couple of years as a physical scientist. And it was his work on the development of the numerical model that I'm going to talk about that really drove a lot of the research that we're going to look at today. Next slide, please. So in the Northwest Atlantic, the spring phytoplankton bloom has a direct impact on the health of the marine food web. The rapid increase in the amount of available phytoplankton feeds the zooplankton, which in turn feeds larger and larger marine animals. Off the coast of Newfoundland, the bloom was observed to take place between February and April in the past, and past work has shown a correlation between timing of the bloom and timing of sea ice retreat. The more recent work has suggested a timing with minimum stratification. And the common theme there is that the increase in fresh water leads to a change in stratification, which is going to influence bloom development. Next slide, please. So when we initially proposed this project, two of the planned objectives were given as written here. We wanted to develop a model relating physical and biogeochemical processes to simulate conditions in the water column leading up to and during the spring bloom. And considering that we are under a changing climate, we wanted to look at how the bloom responds to a variety of hypothetical forcing conditions. This latter one is important when traditional linkages between physical variables and the bloom weaken, for example, due to an ongoing loss of sea ice. So the question I'm putting forward today is, how does our model represent the spring bloom when forced with typical climatological conditions? And what happens when we modify those conditions in some way, for example, making the air temperature warmer? Next slide. To outline the rest of this talk, I'm going to briefly describe the model and the data that we use to force it. Then I'm going to detail a reference simulation forced using climatological conditions from January through to July. And then following that, we're going to modify our forcing in 3 ways to see how the bloom responds when we are using this model. So we're going to increase our winter winds, use overall warmer air temperatures, and shift the freshwater forcing conditions a little bit earlier. Next slide. We call the model that we have been working with SOG-NL, which was branched from SOG, which was a 1D biophysical model developed by Susan Allen's group at UBC to simulate the spring phytoplankton bloom in the Strait of Georgia. We've made some changes to simulate conditions at Station 27, which is about 4 kilometers offshore and 10 kilometers from St. John's. And it's a long-term monitoring station going back decades that is regularly surveyed as part of DFO monitoring missions, particularly the Atlantic Zone Monitoring Program. And the site is strongly affected by the advection of water from the Labrador Current. The governing equations for the physical model are given here, where this cursive V indicates the mixing of the current velocities, temperature, and salinity by the standard KPP formulation. And surface forcing on the physical model is done by wind, air temperature, with some contributions from relative humidity and cloud fraction. Now, the non-turbulent heat flux is scaled down in the column to prevent the water from overheating. And additionally, we nudge the salinity towards the profiles extracted from the Glorious 12 reanalysis product, over a fairly short relaxation timescale. Next slide, please. The BGC model is a nutrient phytoplankton zooplankton detritus model. We're using a single class of phytoplankton with biological parameters based on Thalassiosira nordenskildi. Nitrogen and silicon are the nutrients, with the former being split between ammonium and nitrate, ammonium being consumed first. The equations governing the evolution of the phytoplankton and nutrient profiles are given here. These are mixed as passive tracers through KPP formulation, while phytoplankton also has a sinking term. But I would like to focus on the growth rate. So next slide, please. Which is divided into 3 parts. So we have the cellular division of the phytoplankton, which is going to be either light limited or nutrient limited. We have a natural mortality of the phytoplankton, which is going to be temperature dependent only. And then we have grazing by zooplankton, which in simulations I'm going to show is negligible here. So in each of the nutrient equations, the cellular division term that shows up as consumption of either nutrient by the phytoplankton, then each of these terms also has a temperature dependence that basically says the reaction rate is going to go up exponentially as the temperature increases. Well, phytoplankton's growth rate peaks at 10 degrees before decreasing down to 0 at 18 degrees. Next slide, please. The forcing, boundary, and initial conditions are all listed here. The weather conditions used to construct climatologies were taken from observational data from St. John's Airport and the Canadian Weather, Energy, and Engineering datasets. The temperature and salinity data used for initial and bottom boundary conditions come from the CAST dataset, the Canadian Atlantic Shelf Temperature Salinity dataset, which assembles profiles from a variety of different sources. The nitrate, silicate, and chlorophyll for the boundary conditions and the initial conditions come from bottle data that's been collected as part of the AZMP. And then finally, the salinity profiles, like I said before, they're nudged to climatology of the GLORIES daily mean salinity. And we know that GLORIES does assimilate data from the AZMP, and we've seen that it does a pretty good job of representing conditions at Station 27. So in a typical year, as shown by these TNS profiles from GLORIES, we start in the winter with near freezing salty waters, which gradually warm at the surface and slowly freshen before rapidly freshening a little bit later. And then, as seen in the surface mean chlorophyll, we get our highest chlorophyll concentrations in March, April, and fairly low for the rest of the season. Next slide, please. So on this slide, we've got the reference simulation that I'm going to refer to going forward, which is forced using the climatology I described previously from January to the end of July. In the upper panel, we have the wind and air temperature that force the model in blue and black, and the surface temperature and salinity from the model are given by green and red. The bottom panel is a little complicated, but I'll do my best to explain. It shows the time evolution of the phytoplankton concentration profile is given by the color bar, where cyan represents the surface concentration of chlorophyll to better depict when the bloom is actually happening. The magenta lines indicate the depth of active mixing, while the blue contours denote where the phytoplankton growth rate is equal to 0. So below that contour for most of the year, down around -30, there is phytoplankton loss. Additionally, to the top right, above that contour, there's also phytoplankton loss. Then finally, the hatching indicates if there's nutrient limitation on the growth rate, while no hatching means light limitation. So in the simulation, we have relatively low phytoplankton concentrations before the bloom initiates around mid-February, which gradually increases to a peak at the beginning of May. After this peak, we have a subsurface maximum for the rest of the simulation because the phytoplankton has consumed all the silicon that's been available in the system, as depicted by these hashes there. In general, the phytoplankton concentration increases as the mixing layer depth decreases, and the phytoplankton is primarily mixed at shallower depths for which growth conditions are more favorable. I just want to note that the blue contours that I'm plotting here, they're only plotted at noon every day. So while it looks like the phytoplankton, the mixing layer depth is always within a region of positive growth, there's a diurnal cycle there that I'm going to talk about in the next couple of slides. We can also see a relationship between the mixing layer depth and some of the physical variables depicted above, such as the stronger winds leading to the deepening of the mixing layer depth in about mid-February, which is then followed by weaker winds and an increased stratification due to surface freshening in March and April that leads to an overall shallower mixing layer depth. So this is the first modification that we're going to make to the simulations. We're going to scale up the winter winds by wind speeds by 10, 25, and 50% as shown in the upper panel here. And then the mixing layer depths for each of these simulations respond as you would expect. The stronger winds cause deeper mixing layer depths before they all converge back to the same mixing layer depth once the winds have been scaled back to their climatological values. The increase in the wind delays the bloom initiation and peak, also leads to a higher peak concentration. Next slide, please. Now, the reason we're seeing these lower concentrations when the winds are stronger, which we can see from these plots of growth right here on the right, where red indicates growth and blue indicates loss, is that the deeper mixing layer depth keeps mixing phytoplankton into loss favorable depths, which last longer during the short winter days. As the days become longer and the mixing layer depth shoals, the phytoplankton is primarily mixed and resides in these growth favorable depths for a greater proportion of a given day. Next slide, please. The second set of forcing modifications we're going to consider is warmer air temperatures, which we implement by forcing with the 50th through 95th percentile air temperatures over 93 to 2022. For the reference case through to the 75th percentile, the difference in surface temperatures for those simulations is at most 3, while in our warmest 95th percentile air temperature case, that's a few degrees warmer than even the previous most warm case. These small temperature differences generally only correspond to minor mixing layer differences, which leads to warmer temperatures giving slightly earlier bloom initiations and peaks. And you can see this in these profiles of temperature, salinity, and density on the right. We have these small, couple degree changes in temperature, and because the stratification is primarily dominated by salinity, the overall change in stratification is not too big, and it's the same for each of the simulations. It's similar for each of the simulations. However, in the warmest case, the bloom initiates and peaks much earlier than the other cases, as indicated by these blue lines. And part of the reason for this appears to be an effect of the temperature dependence on the growth rate, which we can see from the bottom panel, which is much higher for this warmest case when compared to the other ones. Next slide, please. Final set of modifications. We're going to shift the salinity profiles that we nudged to a bit earlier, which generally means shifting fresher conditions earlier and earlier. So for the smallest temporal shifts where the surface salinities are still relatively salty, this leads to deeper mixing layer depths as the stratification is weaker, which means lower phytoplankton concentrations and later bloom initiations and peaks. For the largest temporal shifts, we see the freshest water earlier, thus really early strong stratification and shallower mixing layer depths, which mean higher winter concentrations and earlier peaks and blooms. Next slide. And finally, just to sum up, so the bloom initiation, as we've seen in these simulations, happens when the phytoplankton is mixed within depths favorable to growth for a sufficient period of time. And this mixing layer depth is going to be influenced by wind strength and stratification, with the latter being mostly controlled by salinity on the due to freshwater influx when we're talking about the waters around Newfoundland. Here are some additional notes, but I've gone a bit long, so I'll gladly take any questions now.
Do you want to come up to the microphone so Jared can hear you? Thank you.
Hi, it looks like a great process study. I'm a little bit worried about taking St. John Met data directly to Station 27. We know that at least some of the characteristics of at least the wind change very quickly as you move offshore. And I'm just wondering whether you've made any allowances for that or have any way of checking that.
That's a really good question. And it's been a bit since we've looked at different forcing data. So when we had initially started this, we were also forcing with We had also tried forcing with the ERA 5 reanalysis product. And there are obvious differences there, like the change, the diurnal, I guess, temperature difference is going to be smaller, and there was a bit of difference in the wind, but the patterns look the same. At the time, when we were trying to compare to observation, the St. John's Weather Station was giving better results. If we went back now with the modifications that we've made to the model since, I would probably say that ERA 5 might end up doing a bit better than it did before.
Okay, and this was hourly data you were using?
Yes, yeah, hourly.
Okay, thank you.
Thank you so much, Jared. We'll move on to our next presenter. Yes. And Rick, to share your screen.
Do you have your microphone on, Rick? Can you hear us? Ooh. Wow, it's like that. It's like looking in the mirror.
Rick, we're having issues with the sound, so we'll move on and we'll come back to you at the end. So Kyoko Uehashi will be presenting next on examining hydrodynamic connectivity among marine protected areas in Atlantic Canadian waters based on trajectories of bioparticles with various movement capabilities.
Thank you. My name is Kyoko. I'm now at DFO, but this is work that I did when I worked at Dalhousie University with Jinyu Sheng as my supervisor. Bruce Hatcher at Cape Breton University was the other PI. Sarah Smith works for Bruce, and they were in charge of coming up with the biological behaviors. This work was funded by DFO. The development of the circulation model was funded by the Ocean Frontier Institute, and we would like to thank the Digital Research Alliance of Canada, on whose clusters we ran our experiments. So as I think everyone here has heard of, Canada has pledged to protect 30% of its marine space by 2030. We are about halfway there now, and as the government deliberates on which areas to protect next, it would be nice to know the potential connectivities among existing and potential MPAs, so that, for example, if the ecosystem in one MPA is disturbed, then another MPA can, for example, act as a source of larvae for that ecosystem the ecosystem that was disturbed. And the use of numerical models can provide some information on how MPAs can be connected. So that's what we are doing. And we are our main area of interest is the Scotian Shelf. And in this work, we released particles in experiments from 3 existing MPAs. One is called Banque des Américains. It's off the Gaspé Peninsula in Quebec. So that's there. The second MPA is St. Anne's Bank, which is just off Cabot Strait. And the third one is Basin Head, which is off the east coast of Prince Edward Island. And most of this presentation is about passively drifting particles, but in the end, I will talk a little bit about work that we just started on adding swimming behavior to the particles. So there are 2 parts to our methodology. One is the circulation model, and this is something that was developed for another project with 2 other research groups. The circulation component is ROMS, the sea ice component is size. The horizontal grid size in our area of interest is about 6.5 kilometers on each side. We have 40 terrain following layers in the vertical. For lateral open boundary and surface inputs, we are using reanalysis data, GLORIS for the ocean and ice, RFI for the atmosphere. We are also specifying tides from the Oregon State University tidal model at the lateral boundaries. And we also use freshwater input from rivers and also from melting glaciers and tundra. That's mainly off Greenland and Baffin Island. And one thing that is different from our published paper is that for the simulation used here, we are adding methods called the semi-prognostic method and spectral nudging to counteract model drift and bias. And I won't get into that here, but there is a forthcoming manuscript on that work. The model was initialized in September of 2013, and we are using model results from 2015 through 2018. So the other component of our methodology is the particle tracking model. We are using something called ROMSpath. This is an open source model that was developed for use with ROMS output. And we are using seasonal mean simulated currents from 2015 through 2018. So there are 16 experiments for each MPA. And we add something called random walk. So that's small random movements just in the horizontal. And this is to account for movement due to circulation features that the model is forward that the model cannot simulate because the horizontal grid is too coarse. And we set the horizontal diffusivity to 10 meters squared per second. And if I have time, I will get into the effect of this parameter. And we do not add this small random movements in the vertical. And particles are released near the surface from 3 MPAs. They are released in a regular grid. So that means the number of particles released depends on the area of each MPA. And in the following slides, I will be showing snapshots after 60 days or after 90 days that are composited over 4 years. And they are the number, the distribution of particles will be normalized by the total number released over 4 years. So starting with the St. Anne's Bank MPA of Cape Breton. So this is after 60 days. And as I mentioned, for each season, I am compositing the snapshots after 60 days for the 4 years over which the experiments were conducted. And the shading is the percent of particles released in 4 years per square kilometer. And we can see that there is a lot of seasonal variability. And for example, in the summer after 60 days, there is a relatively high concentration of particles of Sable Island, and which is quite intriguing for us because there is another MPA in this area. And also we can see that particles tend to bypass the Atlantic coast of Nova Scotia, which we think might be due to this little gap between the Cape Breton coast and the western boundary of the MPA. So here, as I said, I am just summing everything over the 4 years, but another way to plot these results is to add the outline of these patches for each year. So that's what I'm doing here, and the outlines are color-coded by the years, and we can see that there is a lot of interannual variability too in the particles' movements. And one thing to note is that if we look at spring, and if we look at the 2017 outline, which is this olive green outline, that's when the particles travel the furthest equatorward along the shelf break. And that is going to be our recurring theme for the other MPAs too. So moving on, the next MPA is Banque des Américains, which is off the Gaspé Peninsula in Quebec. And so once again, there is a lot of seasonal variability in how much the particles move. And this time I'm showing the snapshots after 90 days because after 60 days, they're still in the Gulf. And then we can also see that this Banque des Américains MPA can also act as a source area for the St. Anne's Bank MPA, especially in winter. So once again, we can add the outlines for each year. And then once again, we can see that spring of 2017, that's the olive green contour. So 2017 is when the particles travel furthest equatorward along the shelf break. And then the last MPA we're going to look at is Basin Head, which is off the eastern end of PEI. And once again, there is a lot of seasonal variability. Once again, this is 90 days after release, and oops. And sorry, so after 90 days in the summer, none of the particles have made it out of Cabot Strait onto the Scotian shelf, whereas in winter and fall, the particles tend to travel along the coast of Nova Scotia, and then in spring, the particles tend to spread across the shelf. And once again, we see that spring of 2017 is when we see the particles traveling the furthest equatorward along the shelf break. So then we know that the outflow from the St. Lawrence River, I forgot to mention the circulation pattern, but the outflow from the St. Lawrence River is an important factor in the circulation in this region. So I plotted the monthly mean discharge of the St. Lawrence River for the 4 years that we are looking at. This is discharge estimated by a linear regression model from the water level at Quebec City. And we can see that the discharge in 2017 is a lot higher than in the other years. So that's the year when the particles traveled the furthest equatorward along the shelf break. So this is outside the scope of this study, but it does seem that the St. Lawrence River discharge does have a large effect on the bifurcation of the outflow from Cabot Strait and hence on the movement of larvae and juvenile animals in this area. So this was all passive particles, and we have just started working on adding swimming behavior. And right now we're working on diel vertical migration, or DVM. This is behavior that is thought to be undertaken as a predator avoidance strategy. So in standard DVM, animals are near the surface at night to feed, and then in deep waters at night to avoid being seen and being eaten. And for programming DVM in ROMSPAT, we used code that was included in draft form by the developers. So we just cleaned it up and got it to work. So that's the schematic I am showing on the left. And then for the parameters, we try to use values that are relevant to the Scotian Shelf. And for surface irradiance, we are using a temporal mean for our study period from era 5. So that means it is a temporal mean, but it does take into account both the seasonal and interannual variation in the solar radiation. So here I'm just showing results from the St. Anne's Bank 60 days after release. And so once again, there is a lot of seasonal variability. There is a lot of retention within or near the released area in the summer. And then to show the difference between the passive case and the DVM case, I'm showing in this slide just the spring and summer cases. So spring in the top row, summer in the bottom row, with the DVM on the left, just passive particles on the right. So we can see that although DVM is supposed to be or thought to be a predator avoidance scheme, it does affect the movement of particles. So to conclude, I think particle tracking experiments can be useful in determining the locations of potential MPAs and how the existing MPAs interact. And we plan to add more swimming behaviors, release areas, and we hope to repeat these experiments using future projections. Thank you.
Any questions in the audience?
Dave.
Just a quick thought here. You're looking at 60 and 90 days, and in future work, you're thinking of adding swimming behavior, but not being a biologist, I wonder, that seems like a long time for anything to go unmodified by natural, chemical, or biological processes. And I'm thinking, are you thinking of putting any kind, I'm not too sure, you made it very general as to what you're tracking through there, but I'm just wondering, any thoughts on adding more to the model that's going to say, well, if this is a plankton, it's going to die or go to heaven or something in this time. So
yes, so I think once we add behaviors, the passive cases will be only a reference, because I think in nature, larvae are passive for only a few days. That's my understanding. So they're not going, I don't think larvae of any species are actually passive for several months. So the passive cases, I think, will be just for comparison once we add the biological behaviors. And we would like to add settling after a month or so. I think I included that in the future work, so that is planned. So did that answer your question?
Yes, in other words, you are thinking of it. Good.
Yes, thank you.
Any other questions online or?
Yes. I'm just going to read it. Thanks, Nancy, for submitting a question. Thanks for the great talk, Kyoko. I'm wondering, besides the DL vertical migration, are there other factors that influence the vertical motion of the particles?
Well, there is a lot of motion due to advection. If you could, can I, oh, actually, so just the passive particles do undergo a lot of movement. So this is, I think this was, yes, so this was the case from St. Anne's Bank. So the left-hand side is passive particles, and then the right-hand side is DVM particles. So it's depth versus time. So just vertical advection does have a lot of effect on the vertical positions, if that answers your question. And thank you, Nancy. Thank you.
So hi everyone, thanks. I'm Shane. I am currently a master's student at Memorial, and my project, I'm actually working with the DFO. So what we've actually done is they had these acoustic Doppler current profilers deployed off of the coast of northern Newfoundland in Notre Dame Bay. And they've remotely and continuously collected data for the deployment of a whole year between August 2021 and 2022. And the whole question is, well, they deployed them near mussel farms. So they put one in by the mussel farm inside the bay. The other one was outside of the bay, more or less just so we can compare the two. And the big picture question is do these farms affect the wild population? But I'm just a physicist. I'm no biologist by any means, but so I'm more or less interested in the data that we've gotten here. And then once I hand it back over to DFO, they can try and come to some conclusions there and help me with that. So our deployment site, you see up at the top figure here, is all the way up in northern Newfoundland. It's called Notre Dame Bay. It's a little bit west of Lewisport. I don't know if anyone's familiar with that. So both ADCPs were operating at a 300 kilohertz frequency, and they were placed 35 meters below the surface. NDB05 was just a tag put on, and NDB04 was the tag put on the two ADCPs for station IDs. 05 is at the mouth of the bay, so outside. I'll be referring to this one as the outside transducer. NDB04 is the inside transducer. So when I say out, inside, inside, that's what I mean by that. And then the three green stations you see down here. So the bottom picture is just a zoomed in portion of the top one. The mussel farm, the three green stations are just different stations that the DFO went out every month, and they did monthly data sampling of dissolved oxygen and chlorophyll. So with my acoustic data, I did some just comparisons with how it compares with dissolved oxygen and chlorophyll. So just a brief introduction here, nothing too serious about Doppler sonar. So initially you have the sonar that's in the water. You can have them oriented up or down to place, depending on what you want to do. Ours actually were placed 35 meters below, so they were upward oriented, so they emitted sound pulses upward. But this one, you just emit a sound pulse, and it's a pulse pair, which is important. So two pulses travel down through the water column, they bounce off scatters in the ocean, it could be anything, and then that sound is reflected back. And initially is used to measure water velocity measurements, which is correct, but we use it in a different way. So, and Doppler and sonar, you might think obviously is frequency. It measures the change in the frequency, but we don't do that either. We measure the shift in the phase between the pulse pair, and then that shift phase is then goes through a mathematical process called autocorrelation. And then if these things are correlated, then they get coined as, say, a target detection. If there's no correlation, then it's just no target detection. It's just disregarded as volume backscatter. So, and one more thing about the instruments, they need to be calibrated, of course. And down here at the bottom of the screen here, you see this big long equation. That is the volume backscatter equation. And when we calibrate our instruments, highlighted in red down here in the equation is Kc factor. And once we calibrate the instruments, this is the constant we are looking for to plug into our equation, because initially the instrument measures the data in counts, but we want to convert from counts to dB. So that's what that constant here that we, through the calibration process, we calculate, and it goes into our equation. So how do we actually detect a target? So this data, these two plots here, this is not mine. This is what my supervisor graciously gave me permission to use, just as an example. So when I talk about the autocorrelation process, you see up at the top, this is the intensity reading, and you see these bright spots in the thing, in the plot, sorry. These are high intensity points within the data set. And down bottom is a corresponding correlation image. And then you see that the portions, where's the laser thingy here? Perfect. So you have like a high intensity reading here, and then down here you have high corresponding correlation. So these two pieces, the correlation corresponds with the intensity, so these are correlated, so I guess regarded as a fish detection or some sort of target detection. And that is in a nutshell of how we coin what we actually determine the target with. So looking at our volume backscatter data, so so the big spikes here correspond to the volume backscatter, and as we can see inside the bay here, there's like this little secondary peak here, but these big peaks mainly, they're just, most of it is just big volume backscatter or whatnot. And the top figure here is just detected targets or detected targets inside the bay. And then the bottom piece here is just the calibrated intensity. And I just put them side by side just to show that there's so many within the calibrated intensity targets here. There's just so much data that, you know, it's this little tail here toward the end between, I don't know, minus 65 to minus 40 dB. This is what we're actually interested in, because when we look at the detected target data, this stuff here, this is where our predominantly more single fish detections or target detections are coming into play. And whereas here's can be a little noisier. So we're actually more interested in this region here. So I chose a threshold of about minus 65 dB. So anything greater than minus 65 dB, that gets coined as a target detection. Anything less than that, it just gets thrown away as volume backscatter. So I took this little red area of both regions, and I just kind of plotted that, for instance. So outside the bay, you're seeing more of a secondary peak here. So it shows more of a distribution of more, I guess, target detections within the bay as compared to inside the bay here. And what is showing essentially is just the size distribution of our targets within the fish column. And here, this is just some sonogram or echogram, of our target detections. So left is inside the bay, right is outside the bay. The more brighter colors you're seeing, that's more or less what we're getting as fish detections. And we're seeing not a whole lot. They look pretty similar, which is good, I guess. We're seeing sort of, I guess this is sort of like a plankton bloom of sort, I guess you can see. But the most interesting thing we're seeing here is that it seems like there are bigger targets inside the bay as opposed to outside the bay. So we're kind of in the process of investigating that now. And just to get some more information on this, I took that circled region, I filtered our data, and I just plotted histograms of this. So top image is inside, bottom image is outside. We can see our main peak here at around minus 80-ish. It is shifted a little bit, as you can see, as compared from inside to outside. Don't really know what that is quite yet. We do have some suspicions. However, when we do look at this, perfect, thank you, you can see these little secondary humps here, which indicate, again, larger targets. And it's just the distribution of the size of our targets here. And it does seem like there are some bigger ones inside the bay, but mainly there is an overlap between the two regions. And just some more visualization stuff here. We actually took the number of, we call them number of fish, but it's just number of detections. So this is just an example for inside the bay. And this is all I'm here. The only reason I really put this here is just to show that we do have similarities here at the top and bottom. So we have high intensity here and we have high number of fish counts, which we would expect. But we're also seeing points of not much intensity as opposed to highly lots of fish detection. So this is just to show that just because we have points of lower intensity, it doesn't mean we're not detecting fish. And just some, I'm running low on time, so I'm just going to have to zoom here pretty quick. This is just the comparisons with the chlorophyll. We can see some correlations here, but we're having some not so correlated stuff here. So it is correlated in a sense, but it is not entirely correlated because we're getting high chlorophyll counts here, but we're not getting much backscatter here. And then another comparison with dissolved oxygen, we're seeing a correlation here, but it's a negative correlation. So here where we're getting high intensity readings, up around here, we're not getting so much dissolved oxygen. And here we're getting lots of dissolved oxygen, but not so much intensity. So the next steps, of course, would be just to investigate these questions. Okay. And some conclusions. So overall, seems like there's larger targets inside our bay, in around the mussel farms, than there are outside the bay. Comparison with the chlorophyll data shows a little bit of correlation, but not a whole lot. And so, like I said, I'm not a biologist, so I've just done a little bit of reading, but high chlorophyll usually suggests high phytoplankton numbers, which should be an indication of high zooplankton. So you think high chlorophyll would mean high like fish detections, but we're not always seeing that. It's not always the case. And where's my dissolved oxygen too? And oh yes, and our second conclusion, of course, we're seeing a negative correlation with our dissolved oxygen. And lastly, but not least, our acoustico-backdated data is, oh, that's right there. But what I meant to say was that the two data sets, the intensity, they do seem to be fairly similar, fairly the same, which is always good. It's just we see apparent bigger fish or detections in inside the bay rather than outside. So the next steps, of course, the biggest pressing issue would be why are we getting larger targets inside the bay rather than outside? One possible thing we've talked about, it could be a calibration issue within the instrument, and if it is, we have to fix that. And then also compare with plankton surveys. So we'll have to connect with the DFO again and get some more data on plankton surveys within the area. And yeah, so thanks everyone. Or do I just
Thank
leave?
you, Shane. We have time for our one question from the audience or online.
I was wondering about the size discrimination.
Sure.
So I was kind of curious about this. The questions you were talking about, it seemed like something you were making a connection between the size of an object and the frequency, and yet you also were rejecting a certain frequency band as being just volume backscatter. So I wonder if you can dig into that a bit and kind of talk about size, please.
Okay, so size, we're talking about intensity. It's the intensity reading, right? As opposed to the frequency. So I'm not sure if it's here anywhere. So, okay, just for an example here. So for our intensity, so I chose a threshold of minus 65. So typically anything around minus 40-ish, minus 30-ish, you're getting into, let's say, more discrete single targets, or say bigger targets, such as something maybe like a codfish or something like that. We don't exactly know. Anything beyond, anything less than, say, minus 40 or minus 50, you're getting into zooplankton territory, for example, right? So smaller targets, but it's just, and you can get clusters, and you can get clusters of zooplankton. So essentially, in a nutshell, you're getting with lower dB is generally smaller targets, higher dB is generally bigger targets, more like discrete single detections.
And what about movement? If you had, like, say, a cod, for example, and it was moving, would that affect the frequency you would get?
Typically, no, but because they generally move, cod, for example, generally move with the current, and current is not really that fast, especially inside here. It's millimeters per second, right? Or centimeters per second. I can't remember the magnitude, but for more discrete targets, if you're getting moving like that, it's not going to affect it a whole lot. But if you had, say, like a cluster of fish, maybe, and because one pulse comes down, if it moves a certain distance or orients around like that, and by the time the other pulse gets and it goes back to the receiver, then it's not going to show much correlation. So then it will throw away. So that's an issue with the instrument as well, right?
Okay, we need to move on. All right, thank you.
Thanks.
Thank you so much.
Okay, we're going to try again.